what's their transforms the last time. All right. And we,
Sir,
yeah,
um, we kind of lost from last week. I mean, I know the power cut or what happened. And then the video for this for last class, we get it, but you know, I'm the audio. So
mm,
if you kind of give you a brief rundown or what happened because it was a lot, and then the sharp exit from the meeting.
mm. All right. So, well, fortunately for you, although it was a lot, um, it wasn't. This was the setup for today. So, just pay attention to what is going on today. All right. Um, so we had that is a transform for a function was sum infinity z to the minus n times the function. That was the, and we would write that down as z, z transform of the function. Write that down as z fz. Um, so what we want to look at today, we had looked at last time that if I had so if we had to solve we had said that what we would have would what we would have done is that we would have let y be equal to a to the k. That is our test. And we would have ended up with the auxiliary equation um, a squared plus 3a plus 2 equals 0. Um, and that will give us a plus 1, a plus 2 equals 0. And then, so a will be equal to minus 1 minus 2. So our y, k, will be equal to some constant. I'm calling it C1 to the k plus C2 minus 2 to the k. I realize that I switch up variables. So here what? I'm going to call, it doesn't matter what I call it, either in our case, or just to be consistent, I'm just going to put the case. Less case to change the n, so that is why I changed the case. Change it to case. So that was where we, sorry. So that was where we were. And then we had looked at some Z transforms. So let me go and look up Z transform table. And we had looked up some Z transforms. We had calculated some Z transforms last week. But we just want to use this to look at now how we use the Z transform table.
Sir, you said the keys were equivalent to the A or to the N.
N. Oh, equivalent to the n. Well, I just pick out a proper Z transform table for. All right. So let me talk now about what we did subsequent to that. We had talked about finding the Z transform for some. So we found the Z transform for the unit step. And we had gone about doing that. So this was UN and is equal to 1 for n greater than 0. And we said that the Z transform was Z to the minus n, UN, which is equal to 1 from 0 to infinity. So if we wrote out a few terms of that, that would be 1 plus Z to the minus 1 plus Z to the minus 2, etc. And then we use that fact that the sum to infinity of a geometric progression is a over 1 minus r. A is 1 and r is 1 over z, but I multiply by so that I get z over z minus 1. All right, so this result I need you to bear in mind. Okay, so let us look at how we use the z transform to solve a difference equation, because what we said last time was that the difference equations that we had to solve excuse me 1 second. Anybody can look up and tell me what are the two results that we had for these two? I may have had n. So look back and tell me what I had as the result for these two.
Sir, for the
k plus 2,
Mm-hmm.
you have z square, is it f of y of z minus z square.
Mm-hmm.
You hearing me, sir?
Yeah, man, I hear you.
Minus z square f of 0, y of 0 minus z y of 1.
And for this one,
It's z y of z or y of k minus y of y naught y 0.
all right. So what we are going to do is take the Z transform of, so we're going to use these results and we're going to take the Z transform of the two sides of the equation. So we're going to, just like the Laplace transform, we're going to say taking the Z transform of both sides. So we are going to end up, we're going to write for yk of 2, we're going to write z squared y of z minus z squared y of 0 minus z y of 1 plus 3 z y z minus y of 0 and then plus 2 y of z. So we will take the z transform of y of k, we get y of z. 3 times y of k plus 1, so we're going to replace it by what its z transform is. And the z transform of un is, we have z over z minus 1. So we're filling all of the things now. So this is z squared y of z. This term here, y of 0, so y of 0 is 0. So this term here is 0, as well as this term here is 0. So we're going to have z squared y of 1 is 1. So this is going to be minus z plus 3z y of z plus 2y of z is equal to z over z minus 1. First thing I'm going to do is carry over this z here. I'm going to do two things in one. I'm going to factorize out y of z. That's z squared plus 3z plus 2 is equal to z over z minus 1 plus z. Carry this z over to the next side of the equation. So we're going to simplify this side of the equation. So the denominator is z minus 1, and this numerator, z times 1 is z, z times z is z squared, z times 1 is z. So once again, so we have yz times z squared plus 3z plus 2 is equal to z squared over z minus 1. So I'm going to make yz the subject of the formula. So y of z is going to be equal to z squared over z minus 1, z squared plus 3z plus 2, which I can write as factors z squared over z minus 1, z plus 1, z plus 2. All right, so at this stage, this would be very similar to what you would do if you had a Laplace transform. So at this stage, what we would say that you would do is break this up into its Z transform equivalent. I mean, split it up into its partial fractions. So we can write on this inverse Z transform. But the only difference that we do, and I will explain at the end, you will see at the end why we do it, and I will explain, is that we're going to divide both sides by Z. So we're going to have YZ over Z, right? So, and you will see why it is that we do that at the end. So if I divide the this right hand side by z, then that is going to be z, because one of the z square is going to cancel. Z minus 1, z plus 1, z plus 2. And that is what we are going to split into partial fractions. So we are going to have so we're going to write that z over z minus 1, z plus 1, z plus 2 is equal to a over z minus 1 plus b over z plus 1 plus c over z plus 2. So if we take each, we're going to end up with a. When we recombine, it's going to be a times z plus 1, z plus 2. That's a, z plus 1, z plus 2 plus b, z minus 1, z plus 2 plus c, z minus 1, z plus 1 is equal to z. Check and see if we can do that correctly, please. All right.
Yes, sir. Look correct, sir.
All right. Cool. So we're going to let z equal 1 so that we drop out the b and the c. So that's a into 1 plus 1, 1 plus 2 is equal to 1. So that is 2 and 1, 3, 3 and 2, 6. So it implies that a is equal to 1/6. And then we're going to let z equal minus 1. So that's going to drop out a and c. So we're going to get b minus 1 minus 1 minus 1 plus 2 is equal to minus 1. So b is equal to minus 2 times 1 is minus, so it's minus a half. And then let z equal minus 2. So we're going to a and b going to drop out, so we're going to get c minus 2 minus 1 minus 2 plus 1 equal minus 2. So c is going to be equal to minus 2 over, this is minus 3 times minus 1 is minus, that's 3, minus 3 minus 1. Yeah. So we can write y z over z is equal to a move this thing out of the way. All right, so that is A, which is 1/6 over 1 over Z minus 1. B, which is minus a half, 1 over Z plus 1. And C, which is minus 2/3, 1 over Z plus 2. All right, now at this stage is where we write what YZ is equal to. And YZ now would be the same thing, but each at the top of the equation would have a Z. So that's 1/6 over Z over Z minus 1. We know the Z transform for this. That's UN or UK, whichever one we want to write. And the Z transform, Z over Z plus 1. We are going to look up the Z transform for that. And the reason why we split them into partial fractions and then multiply through by the Z in the end is because these are the forms that the Z transform table is written in. Z over Z plus something or Z over Z minus something. The tables are not written for this form. Many of the tables, some of the tables are. So if we look, let me get a table, one that I can see. Oh, you know, let me just bring up the Z transform table. All right, remember to forget this bigger again. I don't know if you can see the table.
You can hold control and use the scroll wheel, sir. The other way. Yeah.
All right, so the parts of the table that we are interested in are just to show you. If you look at the one with the 1 over B that is there, then you notice that the form of it is a bit complicated. So, but the one that says Z over Z minus B, this form is much simpler to work with. So that is the simple reason why we don't use the 1 over Z, but we use the one with Z over. We divide by the Z and then multiply through back through at the end. So Z over Z minus B is B to the N, and Z over Z minus 1 is UN. So we need these two for our inverse transform. So going back to our, we can write, what did we start out with? YK or YN? You're going to have to forgive me. Sometime I'm going to write K, sometime I'm going to write N. So what we had K. Okay. So the solution we write as K. So this says Y of K is equal to 1/6. Now this Z over Z minus 1, remember we said that the Z transform is UN, which is just 1 minus a half. Z over Z plus 1 is minus 1 with the inverse of that to the N minus 2/3. Z over Z plus 2 would be minus 2 to the n. So that would be, this would be my solution. All right, might look a little bit more qualitatively for right like this. You can also write it like that. So that would be my solution for
But sir, we see where you have 1,6 UN. That could be represented as 1 minus 1 to the n. As I see where you have it at minus half to 1 to the n, and as you would have thing there. Why you use UN?
Why use UN?
Yes. Right at the 1,6.
The UN,
Because it could be right
remember,
written as b to the n.
right, but which would be 1 to the n. But 1 to the n is 1.
Okay, so you just.
So that's what the UN represents. UN, remember that the definition for UN is equal to 1 for n greater than or equal to 0 and 0 elsewhere.
Okay.
That's why I'd left it out down here, because sometimes persons see the UN and UN is this mystical function that they don't remember says is 1. It equal to. But this one, 1 UN is equal to. So just you have to bear that in mind. Oh, and by the way, I should, sorry, this is, let me fix up this a little bit more, because each of them should have a UN beside them if I'm writing it like this. So sorry about that. That's 2/3 minus 2 to the n UN. So it says that the sequence starts at 0. Each of them, it started at 0 and 1, 2, 3, 4, 5, 6, it's equal to 1. So you're multiplying this sequence by 0, but it tells you where it starts. It starts at 0 and goes up. So that's what this UN. So these two are equivalent. These two statements are equivalent. So that's why I said you can write like this, or you can write it as the statement below. All right.
Sir, one other thing, sir. So when we get this equation, what we can do with it?
All right. So it's a sequence. So um so let me so let us say that you have your filter or whatever the circuit might be, your oscillator or whatever the circuit is, and then you sample it. T equals 0.01 seconds. What this Y represents is that at T equal, so that's the sampling rate. At T equal 0 and T equal 1 and T equal, so multiply this by 2 and 3, there's going to be a sequence of voltages coming out. This here that we have is what are the voltages at those times. Is let me correct something again. See me write the foolishness. I write YK and then I write N over here. So let me just fix up that. It doesn't matter whether it's K or N, but we have to keep consistent. So, all right. So when N equals 0, what is the value of the output that is here? So you can plug in N equal 0, N equals 0 in both of these, and then you find the value of the output. And when N equal 1, which is at T equals 0.02 seconds, what's the value? You work it out. And when T equals 0.03 seconds, because that's the sampling rate, so the values here yn represent a sequence of whether voltages, currents, forces, whatever it is that you're discretizing, looking at discrete intervals, then that is what this whole sequence here represents. The sequence represents a sequence of voltages or currents or whatever. But once you take the system and look at it at discrete intervals in time, then the whatever the output is will be represented by the sequence that is here. Because as I was trying to point out last week, when I take a circuit and I sample it, I no longer use a differential equation to represent the system. I use a difference equation to represent the system. And so the difference equation, that is what we have to use um, to describe the output of the system. So this Y represents the output of whatever the system is. At the discrete time intervals.
Oh, so sir, all of this is helping us like being able to mathematically describe systems and such.
That is all that this course is about, being able to help you to mathematically describe any system at all that you have, that you look at. You're supposed to be able to do the maths and work out, if I have this as my input, what is my output? Because that is basically um, what engineers are interested in. I build a system so that the input and the output are, when I put in my particular input, then what I get at my output, I'm supposed to be able to look at it and calculate it and describe it mathematically. And so that's why I say that engineers are not limited to um, electrical systems or mechanical systems or chemical systems. There can be in economic systems, in school systems, in any system at all. You're supposed to be able to look at the input, look at the output, and see how you manipulate the system to change it. But you have to be able to mathematically describe the system. And so the difference equation is a mathematical description of a discrete system. All right. So like I have a friend who works at BOJ, and so they only solve discrete difference equations because money is not continuous, it's every day. So that you look at it today, the next time you're going to look at it is tomorrow. You're not going to look at it in as over continuous time. You're going to look at it in intervals of time. So once you discretize the system, as almost every electrical system now is, then you're going to have to describe it with a difference equation and not a differential equation. All right, so that Yn represents the output. And just a note here, Yn describes the output. And all the way back up here, we could just go back up here. The input was 1, or a step input. Now, like I say, step input, when it is 1 volt or 1 amp or 1 farad, or what, well, it wouldn't be 1 farad. That would describe a component of the system. 1 amp, 1 volt, 1 Newton, whatever so this would be the input, and we are saying that, so let us explain. When you put in the input, it's going, the output, the system is going to take it, and what you're going to be required to do is say, what is K when K equal 1 or 2 or 3 or 4 or 5, all right? So the input of the system and YK represents the output. Okay, so over this side, the right hand side, represents the input, and over the left-hand side represents the system. And we need to work out what the output is at any given time. All right, so I'm going to just go straight into the bilinear transform.
Sure.
Uh,
Sir, how would you develop the difference equation for a system?
well, let me talk about the bilinear transform. Last week we just took one and talk about how we develop the difference equation. But all right, so let me briefly go back to that. We had a system. I don't know if it was this, and we said that we took the. I think it was the other way around, but anyhow, it don't matter. So this is 1 over s, and let's say this is 1. So the differential equation is 1 over s so that v out over v in is equal to s over s plus 1. So that says that the differential equation for the system is dv out dt plus v out is equal to dv in dt. Now, if we discretize a system, then we are going to be looking, so let's say the time interval is t equal 1. Every second we are looking at the system. Then when we're looking at the system every second, then we're going to get values at t equal 1, t equal 2, t equal 3. So let's call that v1, v2, v3. And we are going to be finding the gradient at any interval and time. So I just pick an interval in time vk and vk plus 1. So the gradient is going to be vk plus 1 minus vk over the time interval. In this case, the time interval I'm using is 1 second. Plus v out. So these are my v out. So I'm replacing the derivative by the gradient because the derivative represents the gradient. This is v out of k, and this is v in, and the same thing, k plus 1 minus k over 1. And as you see, if we simplify this, we're going to end up with v out k plus 1. These two cancel in this particular equation is equal to v in k plus 1 minus v in k. So this is a difference equation. So whenever we have a system and we look at it in discrete intervals, we replace dv by dt by the gradient function, and we replace the continuous v out of t by v out at k, where k is 1, 2, 3, 4, 5, 6, 7 times the sampling time. In this case, where sampling time I just chose us 1 second to simplify the mathematics. So that is how we end up with a difference equation for our system. We take it and we replace each of the derivatives. So if we had a second d2 v out dt plus dt squared plus this, then we would have to find the derivative of the derivative. So we would have a k plus 2 equation. All right, so the reason I want to go and talk a little bit about the bilinear transform, which has to do with what we're talking about here. So the bilinear transform convert the continuous system to discrete and vice versa. So it is converting a linear system to the discrete and converting the discrete system to back to the linear. And to avoid I was looking for, let me, oh, I had some notes on the bilinear transform, but it is on the next, it is on the other computer here. I can't bother go through all of that. So let me look up some notes that I will post in the group. Not anything grand, but something that I would like you to look up and read about. Let me see if I give me a second there. Computer kind of slow today, so I don't know. Let me try something else. I don't know, the computer kind of slow and trying to find it elsewhere to talk about it. Yeah. All right. Having some difficulty. I didn't want to go through the mathematics, but all right, they are forcing. When I go through the mathematics, you don't understand anything that I'm saying. That's I cannot be held responsible. Understanding what I am saying about the mathematics is not. So let me go. Let me use the board. Like I said, I had some things written up, but did not load it. So let's go. All right. So if I compare the Laplace transform, so that's infinity e to the minus st f of t dt And the Z transform of a function f of n is summation infinity 0 z to the minus n f of n, there's no dn. Then if you look at these two, because the integral is an elongating s meaning sum, and the Greek letter means sum. So this means sum, and this means sum. From infinity to 0, from infinity to 0, f of t, f of n. So so what we would have is that the z and the e to the minus st are related. So one of the things that we write is that z is equal to e to the st. Now, why e to the st? Remember now, t divided by the integral, not the integral, t divided, yep.
So should that be z to the negative n? Or just
No,
z?
no, no. So I'm explaining why it's just, all right, make we, see, I wanted to avoid all of the mathematics. So, all right, if I have z to the minus n is equal to e to the minus st, that would be z to the n is equal to e to the st. If I divide t into intervals of n, then I would end up with z is equal to e to the st over n, which is really what I want to say, z equal e to the st. So that is what I wanted to say. So so now I'm starting from there. So what we are saying is that the relationship between the Laplace transform, so this represents the relationship between the Laplace transform and the Z transform. So the relationship between the two is Z is equal to the e to the st. But problem, this is a nonlinear relationship. And that is like a 4-letter word. Nonlinear is like a 4-letter word. To engineers is a bad word, the first word. Nonlinear, we don't deal with nonlinear. We only deal, everything we deal with is linear. When you're in maths class and they're considered 1 and 2 nonlinear differential equations, you realize how much problems they give. So everything we do has to be linear. So what we have to do is linearize this relationship. All right. If you have a relationship that is non-linear, then one of the things that you want to do is linearize it. Straighten it out. All right. So, anybody remember Maclaurin series? Say yes.
You can remind us, sir.
You didn't say yes.
I mean, yes, sir, but you can remind us, sir.
Okay. So just so so Maclaurin series takes a function at the point 0, and it expresses it as a polynomial. So this is a function, whatever the function is, and this is the polynomial representation. So of what sense is that to us? So if I have a function that is f of s is equal to e to the st, then I want it as, and this is nonlinear. To straighten it out, I am going to take the first two terms. This is y equal mx plus c. So the first two terms in the Maclaurin series are in the Taylor series. You have heard Taylor series?
Yes, sir.
You
Sir, so
say
you're
yes.
using the linearization.
Yeah. So the first two terms represent the linear, how we linearize any function. So we're going to find f of 0, which is 1. When you plug in 0 inside here, anything raised to the power 0 is 1. And then we are going to f prime of s is going to be se to the minus e to the st. So f of 0 what am I doing wrong here now? Am I taking the wrong thing here? S of 0. Or plug in 0 inside it, it's going to be 0. So then supposed to get 1. Give me a second. I'm just thinking whether it should be S or T. Oh, sorry. I just remembered. We have to split this up so that we don't end up with this horrible problem that we have here. That's why I said I wanted it taught as notes, because I just wanted to write down the result. So we have to write e to the minus s, e to the st over 2 divided by e to the minus st over 2. You realize that if you could combine this function, is e to the st. This divided by this would give me back this. This is what we linearize so that we can get a nice. I'm not going to go through all of the mathematics for this. So it's not e to the st we linearize, it's e to the st over 2, e to the minus st over 2. So when we linearize the function, we can use s is equal to, we're going to end up with z is equal to, the linear form of this function is 1 minus st over 2. Sorry, 1 plus st over 2, 1 minus st over 2. And we can make s the subject of the formula. back here a little bit. When we're doing e to the x as a linear function, it's going to be 1 plus x squared over 2 plus x cubed over 3 factorial. So the linear form of this is just that. So if we were to do e to the st, then the linear form of that would be st plus st squared over 2 factorial plus. So the linear form of this would be okay. All right. So, but for the purposes, we don't do the linear form of e to the st, we do the linear form of e to the st over 2. So that's why we end up with this as our z. Like I said, so all of that rambling that you see me there. So let us begin now. So, and I put on back my lecture as well. So when we convert from linear to from z to s continuous to discrete or discrete to continuous, the formula that we use is this one here. Z is equal to 1 plus st over 2, 1 minus st over 2. So that is what we use as our conversion. And we can make s the subject of the formula. So s is going to be equal to, if we make s the subject, I'm not going to work it out on the board. So, but just bear in mind, this is all that I want you to write down from all of the ramblings. This. So convert from discrete to continuous. The only problem that I have is that I don't usually like writing down an equation without giving person some semblance of where it is coming from or what it is coming from. But this one is very problematic because most people don't remember McLaren series, and then most people usually get very confused with all of the ramblings. So don't mind the ramblings, just the thing in the box is what we are dealing with. So don't ask any question about anything else up there, please. And thanks. All right, and then now if we are to convert, if we are to make S the subject of the formula, let me just do that quickly. Outside of, and not putting it on the board. So I'm just going to write it down. Okay, so this one here says it's 2 over t z minus 1 over z plus 1. So if we are to convert I will soon do an example. Convert from continuous to discrete. So this is the other one that we're going to put in the next box. So these are the two things. So actually, this and this is the bilinear transform. All right. So bilinear transform, these two things that are here. I think we can fix up the 1 plus st over 2, 1 minus st over 2 a little bit better. So let me do that now. It's not in a form that you see in the textbook, so I will. So, but I write it down anyway. So we can write this as z. Z equal 2 over t. Let me fix it up a little bit. Again, so we can write it as 2 minus 2 plus st over 2 minus st. All right. So what we're not really concerned with how you get it. We are concerned with how you use it. So let's give an example. So we have a system that is sampled every All right, so we have that system here, and we want to find the transfer function, the z transfer function for the system, not the s, the z. But the first thing that we have to do is find s. So this is my g1, and this is my g2. So we can attempt to And tell me what you get for the transfer function, please.
So what is this? So we have to find the S first and then find the
And
Z.
then after that we use the bilinear transform to find the Z. So I'm just asking you to find the S.
So what's that value above the top capacitor?
1.
One.
So should the capacitors be over S? Just 2.
1 over 2S. 1 over S. 1 over S. It's 2 farad, 1 farad, 1 farad. 1 ohm, 1 ohm.
Which plus one, sir?
You get for G2 now.
Sir, I got 1 over S plus 1.
Alright. So the transfer function for the system is going to be minus 2 over 2s plus 1 s s plus 1. Expand that out, minus 2s squared plus s plus 1. 3s plus 1, sorry. That's what you got?
Yes, sir.
Okay. So now, so to find this Z transform now, we replace S by what we had there. S is equal to 2 over T Z plus 1 over Z minus 1. And we know T is how much? That's 0.1 Z plus 1 over Z minus 1, which my math is correct, Z plus 1 over Z minus 1. So everywhere we see S, we're going to put 20 over Z plus 1, Z minus 1. So GZ now is going to be minus 2 over 2 times 20 squared Z plus 1 over Z minus 1 squared plus 3 times 20 Z plus 1 over Z minus 1 plus 1. And if we have MATLAB, we ask MATLAB to simplify that, but we're doing it by hand for the time being. 800 Z plus 1 squared over Z minus 1 squared plus 60 Z plus 1 over Z minus 1 plus 1. So we're going to put everything over common denominator. That's minus 2. And we're going to use Z minus 1 squared as our common denominator. So this is going to give me 800 Z plus 1 squared plus 60 Z plus 1 Z minus 1 plus Z minus 1 squared. So our GZ would be equal to minus 2 Z minus 1 squared when we flip this all over 800 Z plus 1 squared plus 60. We can multiply this out and we're going to get Z squared minus 1, the difference of 2 squared plus Z minus 1 all squared. So I'm leaving it at that for the time being, but we could, as you can see, we can simplify this even more. which we're not gonna do at this time, but you can't just leave it like that because that is understood. So this is our Z transform. So the bilinear transform is just you're getting the S transform. You have the if you have this continuous time system, you convert it to a discrete time system. And how do you do that? And what do you do to do that? So that basically is what we do with the bilinear transform.
Sir, what can I use this transform to do now, sir?
What you use the Z transform to do, what you use this thing here to do.
Yes, sir. Like, what do they apply to?
All right, so
Remember,
look at this thing that, remember where we started? This is where we started. So this is the system that we are looking at. And it's a discretized system. So therefore, we want a equation to represent my output and my input. So the Z transform and the Z equation is to give me representation between mathematical representation for my between my output and my input. So now, if for example now you are asked the question, so let me write it out this way. So V out over V in. Yeah, I'm writing lane. V out over V in is equal to this equation up here. So suppose you're asked a question, here's a voltage spike on the line, and it's 10 volts. Then my V in, what would be my V in of Z be equal to? And the voltage spike occurred at t equal 2 seconds. What would my V in be? What would I write for my V in terms of Z? Let me write it in terms of K first of all. What would I write it in terms of K?
So is it Z over Z minus 1 or?
Mhm. Z over Z minus 1 would be if I turn on a switch and it was continuous, but it was taking the voltage at different. So that's Z over Z minus 1. I was asking about a spike, one momentary spike.
A bit delta t minus 10, sir.
All right, close enough. So it would be 10 delta because this is a 10 volt spike at t equal 2 seconds. So it's delta t minus 2. So what would the Z transform for that be now? Then go back to the table. Yeah. So if you look here,
So first one.
first one, but that is n, but n minus a, where the thing is the spike at time t equal a seconds, is going to be e to the minus. Sorry, thinking Laplace transform. Sorry about that. It's not e to the minus. What did we say it was?
Sure, Z2 minus A.
Z to the minus a. Yeah, not on this table, but it is z to the minus a. So here's what I'm getting at now. With the question that you asked. So what we have done here is this system that we have. We are saying that this represents the system. We can simplify, when we simplify this and work it out, then we have an equation that represents whatever is happening in the system. Now, you, as the engineering person, if you are asked to say what will happen if how is the system resistant to voltage spikes or whatever, let's say you had a 10-volt spike, how would the system respond? Then you have the Z transform for the system, then you can work out what the system response is going to be. All right, so this we said was what, 10 Z to the minus 2. Also, all right, so let us pursue that. We don't know where it's going to lead us because the example was out of my head. But I'm going to say, all right, what is the voltage going to be like when we have a 10-volt spike at the input at time t equal 2 seconds? So we're going to pursue that and see. So this is z squared plus 2z plus 1 plus 60z squared minus 60 plus z squared minus 2z plus 1. So is equal to minus 2z squared plus 4z plus 2. So 861 z squared, 1600 minus 2 I must make a mistake, so 1598z, and this is 800 minus 60, that is 740 plus 741. So we have our nice and messy. So we are saying if V in is a voltage spike, so we would say now V in of Z is equal to 10 Z to the minus 2. So therefore, it would carry over to the next side. So that would give me V out Z would be equal to 10 over Z squared. I'm multiplying by V in of Z. This is 10 over Z squared minus 2Z squared plus 4Z plus 2. And by the way, like I said, if it's an economic system, then it must be a discrete equation. And the question would be asked, what if I put $10 million on Tuesday, which is day 2 of the week, which is T equal 2? How would the system respond? 10 million US dollars. What would be, how would that respond? How would the exchange rate respond? What would be my output? So is that we're working out general things here and we're assuming that it's electrical, but it can be any system at all. I'm at pains to point out that. All right. So this is our system. So we are going to have this. So let me just simplify this a little bit. Do I have this correct? Yeah. No, I have something incorrect. This should be plus. So this should be minus.
Sir, can you go for a bit so I can take some pictures, sir? After when you find in the Z transform. Alright, sir.
So so this is minus 20 Z squared plus 40 Z plus 20 plus minus. So this should have been changed to minus. So this should have been changed to minus. So this is what my output would look like. And this is what we said the output would look like. So this thing can affect, well, I would be very surprised if this it can be factorized. So here's what I'm going to do at this point. It's a good point. I was going to do it at some other little later down, but we can use MATLAB to help us with our calculations. But I plan to do that a little later down. Let me state. So now we're going to have to split this into partial fractions. And then if we go back to our tables, to find the one that has a quadratic relationship in the denominator, you're going to need bigger tables. All right. I'm not going to pursue it because there's one other thing that I wanted to talk about in closing. And if I sit down and work out this problem, I'm going to be here for the whole day.
So the Z transform would be the transfer function though.
The Z transform is a discrete transfer function for this.
G of Z.
G of Z, yeah. All right. So that this would represent my output, and I would write the A over Z plus B over Z squared plus C Z plus D over all of this quadratic expression here. And like I said, would we can spend the rest of the evening sorting out that problem. Right? But suffice it to say that what the questions that we would be answering is if you have your system and it's a discrete system, whatever it is that you put in at the input, then what is it that you are looking for at the output? And how are you going to calculate it? So we need to be able to manipulate both difference equation and Z transform, which represent difference equation, to be able to work out what is going on inside the system. All right. Um, and we don't have enough of those people in Jamaica, actually, who sit down and study what is going on inside the system and can be able to predict with some amount of accuracy what is going to be the output.
Sir, question, sir.
Mhm.
I know it might come off as a joke, but you know the lottery system is some form of system. Can it be studied, sir?
Of course, of
Because
course.
if we can apply this thing to it, and
The only problem is that they 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 know that the probability of this of getting a particular sequence, they know what it is. But some of the people manipulate this the lottery as well, you know. Because guess what happen? If I have to buy the ticket before, so I have to put in what numbers I want before.
sir, like the box them, sir, the Supreme Ventures box.
No, that's what I'm saying. That you suppose you decide, so you this is pick tree. I mean, I remember when I buy lottery, so I'm not really sure what are the stuff, but you buy a lot of numbers, and so those are that goes into the system to say that I bought those numbers. So and let us say that you have 1 million people buying lottery. Let us say it's the Caribbean one, and you have 1 million people who they know what are the numbers and the combination. So therefore, it can also be manipulated by the persons to make sure say these numbers do not, this number does not come up. That's why I don't buy lottery.
That exact combination.
That exact combination or whatever combination is there. Because once the thing is put in the system and the computer generates it, what are the sequences that are not in the system? Then they can make sure say those things come up
Sir,
easily.
so that's why I have a friend that operate a bar and some of the boxes. So he was saying that the box is like a 20, 75, 70, 30 output. So it mean that it take in 70, anybody will come and gamble at it and then pay out 30% of what it's the input that is taken in.
Mm. The amount that of profit is guaranteed in the system, you know. The amount of money that they're going to make is guaranteed. It's not arbitrary. They know how much money they're going to make per week. All right. Depending on who and the
So
amount of people that they have buying.
so they
And
just need the buyer.
they just
That's
need to
all.
buy. And if you start, it is addictive. If you start and you lose, it is addictive. So you keep on going back because you think so boy a two number we catch, you know, suppose maybe catch the other three. And so and if you ask anybody who gamble, they will tell you say, boy, I'm win more money than so that's why I'm continue. And if everybody win more money than them put in, then the people will be out of business.
So I think the only for the bar and the box, the only person who can win is the person who are selling at the bar. So they can say, all right, this X amount of game played, and
Mm-hmm.
then based on the X amount of game, it is a 40-30 or a 30-70. They can say, all right, the box win 70 game, so it a go payout for the 30%, you know, so them can go play it.
Mm-hmm. But that's what we tell you, say the system is guaranteed. So you can't beat those kind of systems. You can't beat them. So um I my thing is that I don't
Sir, me not gambler either, sir. So, but it's just because we're on the topic of systems.
no man, but it relevant because everything is you can look at as a system. And look at the input and look at what the output is. And look at it over time and you can get what is happening in the system.
Yeah, you have to be careful when you say you're a gamble, you know.
No,
Life
well,
itself is a gambling, I say.
life itself is a gamble. You take a chance to come to university, you take a chance with who you're married, you take a chance when you buy a house, you take a chance when you're going a car. Yes, life itself is a system. And so
But
we have to
life
try.
is not a linear system like that.
No, it is a
It's a non-linear.
stochastic system. Probability. Not no, it's not deterministic. Most people don't want the deterministic part of it, not deterministic. You know, say if I do this, then that must happen. So I am multiplying x by 3. No, it's not 3, it's a probability. Right? So you're saying I will take if I leave Maypen to Mobile, I will it's going to take me 2 hours because I am driving my car. That is only a probability. That is not deterministic. So everything in life is a chance. If I get my degree, then I'm going to get a job that pays me $10 million a year. No, it's not guaranteed. So everything, yeah, you can look at as a system. But and life, like we say, yeah, is a chance. But just like with the dollar, probability of certain things is higher. All right. I just want to mention one last thing. When you have -1 to the k, then if you look at the output, k equal 1, k equal 2 is going to go from negative to positive to negative to positive. It's going to oscillate like that. So k equal 1 is what we call marginally stable. If you have half to the k, first value is going to be 1. The next value is going to be a half. The next value is going to be a quarter. The next value is going to be 1/8, and so forth. So by the definition of stability, this is trending downward. So this system is stable. 2 to the k, on the other hand, the first value is 1, the next value is 2, the next value is 4, the next value is 8. So you see that it is trending upward. So this system is unstable. So a discrete system is stable, and discrete we're talking about now, if and only if the roots of the characteristic equation is less than 1. So if it's a half, we're good. If it is above 1, we have a problem. So it's a modulus of the system that has to be less than 1. So now, every year we say that if you study
Sir,
your
hold on there, sir. Go back up, please. Sorry about that.
want to make a distinction. The condition for stability in a discrete system, the condition for stability in a discrete system is different than the conditions for stability in a continuous system. So please note that the conditions for stability in a discrete system is different than the conditions for stability in a continuous system. So we will just make a
There are
little,
conditions for stability, right?
yeah. So in a continuous system, you will draw it neat. By the way, while we're talking about systems, the, this why the whole entire world is in lockdown is because somebody at the University of London built a model that said by the, by this time now you should have had how much million people. Well, in Africa, yeah, we were supposed to have 8 million people dead. In Britain, you're supposed to have 1 million people dead. That was the model that he put together, a discrete modeling put together, because he's in charge of modeling. So, and his model said how much people were going to die from this disease in how many months. So the only thing that you can do, since we're in such a calamity, is to lock down the whole entire place and lock down everything and tell everybody to stay home. That is the only thing that could have saved millions and millions of people from dying. His model was proved to be grossly incorrect, but the policy is still in place. So that is why everything is still as it is. And just like Columbus, when Columbus sailed west, he thought he was in India. So that's why we are the West Indies, even today. So when these Europeans make their calculation and make the mistake, we still have to pay. We still end up paying for it because they're not admitting that there is a mathematical error made. How could the brethren from Imperial College London make a mathematical error of this magnitude? But persons have said that he has made the error before, made errors before. And if anybody remember mad cow disease, he was the one that built the mud land and killed off all the cow them in England. Anyhow, if you can look him,
more coffee we sell them.
well, but we in a lockdown because of him, because him say do whatever you did. So let me just draw in a diagram. The what I have over on the left hand side is supposed to be a circle. So if we are saying that if it is in poles are inside of the roots of the characteristic equation are inside the unit circle, the system is stable. For continuous system, we say that the roots have to be negative. So the poles so discrete system, continuous system. So we can look at it and we can look at it and see that it's two different conditions. One, the modulus has to be less than 1, so it has to be inside the unit circle. One, the root has to have a negative real part for it to be stable. So these are the two different conditions. And the people who don't study, we ask about them every year. And because you only read the first part of the notes, everything is there to that continuous system.
Sir, can you go back up for a second, sir? Okay, thank you, sir.
Okay.
So when you put poles, not so sure what the poles represent. So,
Okay.
um,
All right, so we ask the question, is the system represented by gz equal 2z, z squared 4 over 2z, 4 over z squared plus 2z minus 8. Let me put plus 8, make it more interesting. If that is stable or not. So, what we mean by the pose or characteristic equation is z squared plus 2z plus 8 equals 0. So our z is equal to minus b, which is minus 2, plus or minus square root of b squared, which is 4, minus 4 times a times c, which is 8, all over 2a, 2 times 1. So that's minus 1 plus or minus with 32 minus 4 is minus 28 over 2. So it is minus 1 plus or minus the square root of 7. So now, if it were s, then fine. This would mean, this negative one would mean that it is stable. But this is not s, it is z. So these are my poles of the system. The characteristic equation, the denominator of the transfer function equals 0, and my poles, the negative 1 plus or minus root 7. So what I have to do is find the modulus of that. So the modulus of a complex number, if it is a plus b j, the modulus is a squared plus b squared. So the modulus of z for this particular one is square root of minus 1 squared plus root 7 squared. So that is square root of 8 and we know that that is bigger than 1. So the system is not stable.
Sir,
Hello?
yeah,
I never hear anything at all on the quite.
All right. So it doesn't matter if you're dealing with a marginally stable or a stable, as long as it's not unstable.
All right. Now there are times when you want marginally stable because you suppose you want to design an oscillator, then you want the system to be marginally stable. All right.
Oh,
So
all right.
sometimes you want the system to be stable, sometimes you want the system to be marginally stable. I don't know of any time when you want the system to be unstable. All right. So it depends. If you want an oscillator, for whatever reason, you have a whole lot of reasons why you'd want an oscillator in the system, then you'd want it to be marginally stable. All right. Much has been said, so I'm going to stop it there for this evening. Um, I'm not sure about class next week because somebody asked me to play at the funeral of their husband at camp, so I don't know what the setup is going to be like.
So you're a musician, sir?
No, I fiddle around the keyboard.
Good. So no other sister.
Yeah, me not a musician. No, I know.
You're full of talent though, man.
No, I
I'm
can't
just
handle myself.
going to tell us if you want to listen, sir.
Eh, eh.
All right, boss.
We can teach anybody for well.